Welcome to this problem-solving session. Today, we'll dive into LeetCode problem number 156, binary tree upside down. Together, we'll explore the problem requirements, analyze its unique characteristics, and develop an efficient solution. Let's get started. In this problem, we are asked to take a binary tree and turn it upside down. What does that mean? Essentially, we need to restructure the tree so that the leftmost node becomes the new root. Additionally, the original root becomes the right child of this new root, while the original right child becomes the left child of the new root. This transformation is applied recursively, starting from the leftmost node of the tree. The input to the problem is the root of the binary tree, where each node contains an integer value, as well as pointers to its left and right children. The output will be the root of the transformed tree, now turned upside down to follow the described rules. To better understand, let's take a look at an example. For the given input tree, where the root has the value 1, and its left and right children have values 2 and 3 respectively, the structure also extends further with node 2 having children 4 and 5. After applying the upside-down transformation, the result is a new tree. The leftmost node, 4, becomes the new root. Node 5, which was the left child of 2, becomes the left child of 4. Simultaneously, node 2 becomes the right child of 4. Continuing this process, node 1 becomes the right child of 2, and node 3, which was originally the right child of 1, becomes the left child of 2. The output of this transformation, represented as a list, is 4, 5, 2, null, null, 3, 1. Here, we can visualize the transformed tree structure. Node 4 is now at the top, serving as the new root. Its left child is node 5, and its right child is node 2. Moving further down, node 2 has node 3 as its left child and node 1 as its right child. This restructuring follows the rules we discussed earlier. The original leftmost node, 4, is now the root, while the relationships of the other nodes are rearranged accordingly. This recursive transformation ensures that each subtree is flipped in the same way, maintaining the specified constraints. Now, let's look at another example with a simpler tree. In this case, the root is node 1, with nodes 2 and 3 as its left and right children, respectively. After the transformation, node 2 becomes the new root. Node 1, which was the original root, becomes the right child of node 2, and node 3 becomes the right child of node 1. The resulting tree is structured so that node 2 is at the top, with its right child being node 1, which in turn has node 3 as its right child. The output for this transformation is represented as 2, null, 1, null, 3. Looking at the explanation for this example, we can see the tree's transformation step by step. Node 2 is now the root, as it was the leftmost node in the original tree. Node 1, the original root, becomes the right child of node 2, and node 3 shifts to become the right child of node 1. This process adheres to the rules of the upside-down transformation. For an even simpler case, such as an empty tree where the root is null, the output will also be null, since there is nothing to transform. An empty tree remains unchanged. To summarize, the problem comes with specific constraints that guide the transformation process. The binary tree will always be a full binary tree, meaning every node has either 0 or 2 children. The number of nodes in the tree can range from 0 to 10,000, and each node's value will be between -100 and 100. When considering edge cases, an empty tree remains empty after the transformation. Similarly, a single-node tree will remain unchanged since there are no children to rearrange. For trees that are already skewed, such as those with only left children, the transformation will not significantly alter the structure. These constraints and edge cases help to clarify how the function should behave in all scenarios. To solve problem number 156, binary tree upside down, the goal is to transform the given binary tree into its upside down form while maintaining the constraints of the problem. Several approaches can be considered. The first is the recursive approach, which leverages the natural hierarchical structure of binary trees. In this method, we recursively traverse down to the leftmost node, which will become the new root of the upside down tree. During the backtracking phase, we adjust the pointers so that the current node's left child points to its right child, and the right child points to its parent. It's also important to nullify the original root's left and right pointers to prevent cycles in the tree. A key insight here is that the leftmost child becomes the new root, and the relationships between the original nodes are reassigned accordingly. This approach is efficient because it uses the call stack to manage parent-child relationships, avoiding the need for additional data structures. Another option is the iterative approach, which avoids recursion by using explicit pointers. Here, 3 pointers, parent, current, and right, are used to track the current node, its parent, and its right child, respectively. This setup allows us to iteratively reassign pointers according to the transformation rules. Once the current node's pointers are updated, we move the current pointer to its left child and continue the process until all nodes have been processed. By maintaining these explicit pointers, the iterative method performs the transformation in place without relying on the call stack, making it a better choice for very large trees. Like the recursive method, it has a time complexity of O(n), but its space complexity is reduced to O(1), as no additional storage is required. A less optimal alternative is to use a stack to simulate recursive backtracking. While functional, this approach is less efficient since it requires additional space proportional to the height of the tree, making it less desirable compared to the recursive and iterative methods. The recursive approach was chosen as the preferred strategy due to its simplicity and alignment with the problem's constraints. This method intuitively mirrors the structure of the problem. By traversing to the leftmost node first, we naturally identify the new root of the upside-down tree. During the backtracking phase, the necessary pointer adjustments are made without requiring extra memory for explicit stacks or other data structures. The decision to favor this approach stems from its clean and concise implementation, which is easy to understand and debug. Additionally, it achieves optimal space efficiency by relying on the call stack for backtracking. However, it's worth noting the trade-offs. Recursion can lead to stack overflow in cases of very deep or unbalanced trees. For such scenarios, the iterative method becomes the more robust alternative. While the iterative approach avoids the risk of stack overflow, the added complexity of managing multiple pointers can make the code less readable and harder to maintain. In conclusion, the recursive approach stands out for its elegance, readability, and close alignment with the problem's constraints. It provides a straightforward and efficient way to transform the tree while maintaining an optimal time complexity of O(n) and minimal space usage. For extremely large or unbalanced trees, the iterative solution offers a practical alternative, as it eliminates the risk of stack overflow. Both methods are efficient, but the recursive approach is generally preferred for its cleaner, more intuitive code. By understanding the strengths and trade-offs of each approach, you can select the most appropriate solution based on the specific characteristics of the input tree. To solve the problem of flipping a binary tree upside down, we need to carefully transform its structure. The goal is for the leftmost leaf of the tree to become the new root, and for the rest of the nodes to be rearranged accordingly. Here's the detailed breakdown. First, in an upside-down binary tree, the leftmost leaf becomes the new root. Then, each parent node becomes the right child of its left child, while the original right child becomes the left child of that same left child. This transformation continues recursively until the entire tree has been processed. To implement this recursively, we start with a base case. If the input tree is empty or contains only one node, it's already in the desired form, so we simply return the root. In terms of the base case condition, if the root is null or the root's left child is null, we return the root as is. Once we've accounted for the base case, we move on to the recursive processing step. Here, we recursively process the left subtree of the current node. This ensures that we reach the leftmost node first, which is crucial because that node will serve as the new root of the transformed tree. The recursive step involves a key function call, newRoot equals upside down binary tree, root.left. This ensures that we process the leftmost subtree first and identify the new root. Once we've processed the left child, we can start rearranging pointers to achieve the transformation. First, the left child's left pointer is updated to point to the original right child of the current node. This means the original right child now becomes the left child of the left child. Next, the left child's right pointer is updated to point to the current node, effectively making the current node the right child of its own left child. To prevent cycles in the new tree structure, we must set the current node's left and right pointers to null. This step is critical to ensure that the original tree structure is completely detached. Finally, after all these operations, we return the new root, which propagates back up the recursive stack to complete the transformation for the entire tree. Let's look at the final implementation of this algorithm, which ties all these steps together in code. The implementation begins with the base case check. If the root is null or has no left child, the tree is already transformed, so we return the root. In the recursive step, we process the left subtree by calling the function onRoot.left, which gives us the new root. After rearranging pointers as described earlier, we set the current node's left and right pointers to null to finalize the detachment. The function then returns the new root that will propagate up the recursion stack. Now, let's discuss some key insights about this approach. The recursive nature of binary trees is fundamental here. By processing the left subtree first, we ensure that the leftmost node becomes the root before rearranging other nodes. Pointer reassignment is the core operation, and understanding how parent-child relationships shift is crucial to implementing this correctly. Another important aspect is that this transformation is performed in place. We don't create new nodes or use additional data structures, which minimizes memory usage. The only space overhead comes from the recursion stack, making this an efficient solution overall. This is especially important when dealing with large trees. The algorithm efficiently flips the binary tree in place, requiring no additional data structures. The recursive call ensures that we reach and process the leftmost node first, which becomes the new root. By carefully reassigning the left and right pointers of each node, we achieve the upside-down transformation. The base case check prevents unnecessary operations when the tree is empty or contains only one node. When analyzing complexity, the time complexity is O(n), where n is the number of nodes in the tree, because each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursion stack. Edge cases are an important consideration. If the input tree is empty, the function returns null. For a single node tree, no transformation is needed, and the root is returned as is. Additionally, the approach handles unbalanced trees naturally, since it processes based on the presence of a left child. These edge cases ensure the algorithm is robust and can handle a variety of input trees. Finally, if a node has no left child, the function simply skips any rearrangement for that node and returns it as is. This condition ensures that the algorithm gracefully handles trees where some nodes may lack a left subtree. By focusing only on nodes with a left child, we avoid unnecessary operations and maintain the efficiency of the process. This completes the transformation logic and guarantees that the tree is flipped correctly, regardless of its initial structure. This Python implementation solves the problem of flipping a binary tree upside down. The goal is to make the leftmost leaf the new root of the tree, while rearranging the nodes as described in the problem. The process is implemented recursively in the upside-down binary tree method. First, the treeNode class represents the structure of a binary tree node, with val as the node's value and left and right as pointers to its children. The solution class contains the method to perform the transformation. The recursive function upside-down binary tree accepts the root of the tree as input. The base case checks if the root is none or if it has no left child, indicating it's the leftmost node. If so, the function simply returns the root as the new root of the flip tree. The recursive call self.upside-down binary tree, root.left, flips the subtree rooted at the current node's left child. Once the left subtree is flipped, the current node's right child becomes the new left child of its left subtree, and the current node itself becomes the new right child. These assignments are performed by root.left.left equals root.right and root.left.right equals root. Finally, to ensure the current node is disconnected from its children, root.left and root.right are set to none. This prevents cyclic references and maintains the integrity of the flipped tree. The method returns the new _root, which is the result of recursively flipping the leftmost subtree. The recursion ensures that the entire tree is processed in a bottom-up manner, resulting in the desired upside-down structure. This approach efficiently transforms the tree with a time complexity of O(n), where n is the number of nodes in the tree, as each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. Here, we begin the implementation of the upside-down binary tree method. First, we define the treeNode class to represent the structure of a binary tree node, which includes an integer value and pointers to its left and right children. The main function, upside-down binary tree, takes the root of the tree as input. We start by handling the base case. If the root is null or if it does not have a left child, we simply return the root as it is already in the desired form. Next, we make a recursive call to process the left subtree. This recursive process helps us traverse all the way down to the leftmost node, which will eventually become the new root of the flip tree. After obtaining this new root, we begin flipping the current node. The original right child of the current node is reassigned to become the left child of its left subtree, and the current node itself is moved to become the right child. We then disconnect the current node from its left and right children by setting both pointers to null, ensuring the original structure is broken and no longer interferes with the flip tree. Finally, we return the new root, which propagates up through the recursive calls. This way, each level of the tree gets flipped correctly, and the entire tree is transformed into its upside-down form. The method is now complete, and the recursive approach ensures that the solution is both elegant and efficient. Here, we start with a simple binary tree that has two levels. The root node is 1, with left child 2 and right child 3. To flip the tree, we begin at the root, which is node 1. Since it has a left child, node 2, we make a recursive call with root.left. Now, node 2 becomes the current root. At this point, node 2 has no left child, so it becomes the new root of the flip tree, and we return node 2. Returning to node 1, we proceed with the flipping steps. First, we set root.left to root.right, which means node 2's left child is set to node 1's right child, node 3. Next, we set root.left.right to root, so node 2's right child becomes node 1. Finally, we disconnect node 1's children by setting root.left and root.right to none. The flip tree now has node 2 as the root, with node 3 as the left child and node 1 as the right child. The flip tree from the previous steps gives us the final output for this example. Node 2 is the root, with node 3 on the left and node 1 on the right. Moving to the next example, we now work with a binary tree that has 3 levels. The root is node 1, with left child 2 and right child 3. Node 2 itself has 2 children, node 4 on the left and node 5 on the right. Starting at the root, node 1, we see that it has a left child, node 2. So, we make a recursive call with root.left and continue processing node 2. Now, the current root is node 2. Since it has a left child, node 4, we make another recursive call with root.left. At this point, node 4 becomes the current root. Node 4 does not have a left child, so it becomes the new root of the flipped subtree, and we return node 4. Returning to node 2, we perform the flipping steps. First, root.left is set to root.right, meaning node 4's left child becomes node 2's right child, which is node 5. Next, root.left.right is set to root, so node 4's right child becomes node 2. Finally, node 2's children are disconnected by setting root.left and root.right to none. At this stage, the subtree rooted at node 4 has node 4 as the root, with node 5 on the left and node 2 on the right. Returning to node 1, we now perform similar flipping steps to continue the process. At node 1, we set root.left to root.right, meaning node 2's left child becomes node 1's right child, which is node 3. Then, root.left.right is set to root, so node 2's right child becomes node 1. Lastly, we disconnect node 1's children by setting root.left and root.right to none. After completing these steps, the final flipped tree emerges. The root of the flipped tree is now node 4. Node 4 has node 5 as its left child and node 2 as its right child. Node 2, in turn, has node 3 on the left and node 1 on the right. This completes the flipping process for the 3-level tree, and the final output reflects the fully transformed structure. Finally, let's consider the simplest possible binary tree, a single-node tree where the root is node 1. Since this node does not have a left child, no flipping is required. In this case, the root remains as it is, and the flipped tree is identical to the original tree. The final output is simply node 1, unchanged. This concludes the solution walkthrough for the binary tree upside-down problem. The time complexity of the upside-down binary tree function is O(n), where n represents the number of nodes in the binary tree. This can be broken down into 2 primary components. First, the function performs a recursive traversal of the tree, specifically traversing the left subtree. Since each recursive call process is one node, and there are n nodes in the tree, the recursion will be invoked exactly n times. Second, for each node, the function adjusts its left and right pointers. These pointer updates are constant time operations, or O(1), and since they're performed once for each node, this results in O(1) work per node. When we combine these two factors, the O(n) traversal and the O(1) manipulations for n nodes, the total time complexity becomes O(n). Now, let's consider the space complexity of the function, which is primarily determined by the recursive call stack. The depth of the recursion depends on the height of the binary tree. In the worst-case scenario, where the tree is completely skewed, the height equals n, leading to O(n) space usage. On the other hand, in the best-case scenario of a perfectly balanced tree, the height is log n, resulting in O log n space usage. Importantly, no additional data structures are used in this solution, as all pointer manipulations are performed in place. This makes the space complexity highly efficient. When compared to a brute force approach that might involve creating new nodes and rebuilding the tree, this in-place transformation saves considerable space. While a brute force method could require O(n) additional space, this solution achieves the same goal with no extra memory allocation beyond the recursive stack. To summarize the time and space complexity across different scenarios, the best case occurs when the tree is balanced. In this scenario, the recursion depth is minimized, leading to a space complexity of O log n, while the time complexity remains O(n). In the worst case, where the tree is completely skewed, the recursion depth equals n, resulting in both time and space complexities of O(n). For an average binary tree, the height typically falls between log n and n, meaning the space complexity will range from O log n to O(n). Regardless of the tree structure, the time complexity consistently remains O(n), as each node is visited exactly once. Mathematically, this is justified because the function processes n nodes, performing O(1) work per node for pointer updates. Thus, the total work done is n multiplied by O(1), which simplifies to O(n). The space complexity, however, varies with the tree's height, making it dependent on whether the tree is balanced, skewed, or somewhere in between. When working on this problem, there are a few common mistakes to watch out for. First, there's often confusion about the tree structure transformation. Many people misunderstand how the left subtree nodes become the new root and how the left and right pointers are updated during the process. This misunderstanding can lead to incorrect pointer assignments, ultimately breaking the tree structure. To avoid this, it's helpful to trace the transformation step by step using a small example tree. Another frequent mistake is forgetting to set null pointers for the original root's left and right children after rotation. If these dangling pointers aren't reset, it can lead to memory leaks or incorrect outputs. Make sure to explicitly set root.left and root.right to null during the reassignment. Lastly, overcomplicating the recursion base case is another pitfall. Some people add extra conditions that aren't necessary or forget the base case entirely, which can result in infinite recursion or overly complex code. The base case is simple: if the root is null or a leaf node, just return it. Keeping this in mind will help keep your implementation clean and correct. Another issue that arises is writing an inefficient iterative solution. This happens when extra data structures like stacks are used, which increase space complexity and deviate from the problem's requirement for in-place transformations. Instead, you should use a simple while loop with temporary variables to manage the pointer updates directly. It's both space efficient and aligns with the problem's constraints. Additionally, skipping edge cases during testing can lead to undetected bugs. For instance, a single-node tree or a tree with only left children are simple but critical scenarios that often reveal flaws in pointer reassignment. To avoid surprises, always test with diverse examples, including edge cases like degenerate trees that resemble linked lists. A thorough testing strategy ensures that your solution is robust and reliable. This problem is widely used in interviews to evaluate your understanding of tree traversal, pointer manipulation, and recursion. One key insight is that the transformations here are conceptually similar to reversing a linked list, where you iteratively or recursively rewire the pointers. To stand out, it's essential to demonstrate clarity in explaining how the pointers are updated at every step. For example, clearly describe the tree structure before and after the transformation, and if possible, use diagrams or examples to help your interviewer visualize the process. Additionally, be prepared for follow-up discussions about iterative solutions and their trade-offs. While the recursive solution is more straightforward, the iterative approach is space-efficient, so understanding both is valuable. Lastly, you might want to explore related problems like reversing a linked list, flattening a binary tree, or inverting a binary tree, as these share similar patterns and concepts that can deepen your understanding. There are three main approaches to solving this problem, each with its own trade-offs. The first is the recursive approach, where you traverse the left subtree recursively, reassign pointers for the current node, and propagate the changes up the stack. This method is elegant and easy to implement, but it uses O(h) space due to the recursion stack, where h is the height of the tree. The second approach is iterative, which involves using a while loop to traverse down the left subtree and rewiring pointers as you go. This is more space efficient since it avoids recursion, but it can be harder to follow because of the multiple temporary variables involved. Lastly, there's a hybrid approach, where you combine recursion for traversal with iterative pointer updates, often using a stack. While this method offers flexibility, it can be suboptimal because it introduces extra space usage unnecessarily. Choosing the right approach depends on the constraints and requirements of the problem at hand. Great work! Today, we transformed a binary tree using recursion and analyzed its performance. Remember to practice similar problems to master tree transformations. Thank you for watching, and we hope to see you in our next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!